let's talk about linear algebra. I will start with the concept of an eigenvalue. So we are given a square matrix A, which is an n by n matrix. And the concept of an eigenvalue is only defined for square matrices. So it's important to highlight that we are talking about a square matrix. For rectangular matrices, we will later talk about singular values. So I will discuss this in this video. But first, let's talk about what is an eigenvalue. So an eigenvalue is lambda here, which we denote. So we denote this eigenvalue by lambda, which is a scalar. And we say that lambda is an eigenvalue of A, and V is a corresponding eigenvector of A. So we have a pair. We have this pair of eigenvalue and eigenvector if the following definition holds. So we have that AV. So what is AV? It's a matrix A times a vector V, right? So we have, as a result, this is a d-dimensional vector. And we're asking that this d-dimensional vector is essentially V itself times this eigenvalue. Okay, so the eigenvalue here, let me highlight this. This acts as a scalar. It does not change the direction of the vector, right? So we are saying that AV is supposed to have the same direction as the vector V, and we can multiply it. We can multiply here by a scalar that changes the scaling of the vector. So any lambda V that satisfies this equation will give us one eigenvalue eigenvector pair, and we can have actually n of those eigenvalues and eigenvectors. So if you move this here to the left-hand side and you factorize V, so you can rewrite this equation as this equation here. So again, here I is simply the identity matrix. Or equivalently, you can write it as a determinant of this matrix here being equal to 0. As a quick reminder, the determinant of a matrix, for instance, let's say a 2 by 2 matrix with entries A, B, C, and D, which we also denote. We also denote this in this way sometimes. And this is simply equal to A times D minus C times B. Okay, so A times D minus C times B. All right, so this is yet another equivalent definition, either this or this. I'll give you an example in a minute. One convention that I want to highlight is that we typically assume that the eigenvalues are sorted. So we are saying that lambda 1 is the largest eigenvalue, and lambda n here is the smallest eigenvalue. Okay, this is a convention that I'll be using. Okay, let's look at an example of eigenvalues for some 2 by 2 matrices. So let me first give you, for instance, this matrix here. And here you should pause for a minute and think about what are the eigenvalues of this matrix. So if you did this, and perhaps you already know this, but when you have a diagonal matrix, essentially you can read out the eigenvalues here. So simply lambda 1, which is the largest eigenvalue of A, is equal to 2. Lambda n, which is the smallest eigenvalue of A, is equal to 1. You can verify this, right? You just have to calculate the determinant, as we said, of the matrix A minus lambda I. So let's do it. So here we have 2 minus lambda times 0, 0 here, 0, and 1 minus lambda. And again, we want the determinant of this matrix. So this is simply equal to 2 minus lambda times 1 minus lambda. And again, we want to set this to 0, right? So it's clear that I have two solutions, right? I have lambda equal 2 is a solution and lambda equal 1 is a solution. Okay, so here it was fairly easy. Let's do another example, which is a little bit more complicated. So let's take a matrix A with entries 1, 1, 2, minus 4. So we have to repeat the same, right? So we want a determinant of A minus lambda I. This is equal to 1 minus lambda, 1, 2, minus 4, minus lambda. Oops, actually what I wanted is something a bit different. Excuse me, minus 2, 4. Let me correct it here. Minus 2, 4. minus lambda. Okay, so on the determinant of this matrix. So this is simply equal to 1 minus lambda times 4 minus lambda, right? So this times this minus this, oops, this times this, okay? So minus minus is plus, so we get plus 2. Let's develop this. So what do we get? So we get 4. So let me order them. So we get lambda squared minus 4 lambda minus lambda. So this is minus 5 lambda. And we get a plus 4 and a plus 2, which is plus 6. And now we need to set this to 0. And then if you check, you can see that this is simply equal to lambda minus 2, lambda minus 3. Okay, so the 2 and 3 give you the 6. The minus 2 lambda minus 3 lambda will give you minus 5 lambda. And here you see you have the lambda square. So now the eigenvalues of this matrix, we conclude that the largest one is equal to 3, and the smallest one, number 2, is equal to 2. Okay, so here's an example of how we can calculate the eigenvalues, and you could also calculate the corresponding eigenvectors as well, right? You just have to find eigenvectors that will satisfy this definition here. So concretely, if you want, what you will need to do, and it's a good exercise, is that you will plug, you would choose a value of lambda. So for instance, here you would just say lambda equal 2, and then you would have to find the eigenvector that corresponds to, that solves this equation if you want. Okay, let me move on to another important concept, which is the trace. So the trace is defined for square matrices. We denote this as this TR of A here, and it's simply equal to the sum of the diagonal elements. So let's, as an example, look at our A matrix, which is again n by n matrix. So we have, we write it in this way, right? So we have A11 up to ANN entries, right? So n square entries. And the trace, so as we said, right, the trace is the sum of the diagonal elements, right? So that means that we're essentially just summing those diagonal elements here. So here you just have a sum from I equal 1 to n, and you just summing all the entries on the diagonal. Equivalently, the trace is also equal to the sum of the eigenvalues. So that means that you can write the trace here in this way, right? So you're summing over the n eigenvalues of the matrix. The trace has some interesting and useful properties. So one of them is linearity. So if you take two matrices, two square matrices, A and B, and two scalars. So let's ignore the scalars for now. Let me just remove them. What we have is linearity, which means that if you take the trace of A plus B, it's equal to the trace of A plus the trace of B. Okay, so it's a linear, it has a linear property. And then on top of that, you can add these scalars here. So as I said, we have two scalars, and then you can see that you have that the scalars actually come outside of the trace. So you get this alpha times trace of A plus beta times trace of B. The second property is the cyclic property. So what it says is that the trace of AB is equal to the trace of BA. And it's important not to confuse that, not to say that AB is equal to BA, right? We said that when you multiply two matrices, this is not true. But the trace has a so-called cyclic property, which means that you can take either the first entry and move it to the end, or the last entry and move it to the beginning. To be concrete, if I have, for instance, a trace of A times B times C, so I have three matrices, I can take, for instance, the C and move it to the beginning. So I could write that this is a trace of CAB. However, what I cannot do is say that this is equal to the trace of, so I cannot, for instance, just take the B and swap it with the A. So this is not equal in general to the trace of B times A times C. Okay, so it's really a cyclic in the sense that you cycle something here from the end to the beginning or from the beginning to the end. And you can cycle multiple times, of course. Right? So now here you could take the B and you could move it to the beginning. But again, you cannot swap matrices. This is not true in general. And finally, the last property is that the trace of a transpose, the trace of a transpose is equal to the trace of A itself, right? And this is logical if you think of the definition. When you transpose, the diagonal doesn't change. So of course, the trace does not change. All right. One note on something that is called the Loevner order. So first of all, let me redefine what is a PSD matrix. So PSD means positive semi-definite. And it means that if I take my matrix A and I sandwich it between this vector U, so I do U transpose A U, right? So, and again, U transpose A will be a vector, right? So U is a d-dimensional vector. Let me actually here, for the sake of, for just use because I used N before, so let me change this D to N. So when we do U transpose A U, essentially we are asking that this is always positive for all vectors U. And this is a so-called positive semi-definite matrix. And equivalently, this is saying that the eigenvalues of our matrix are also non-negative, okay, for all the eigenvalues. And if this is true, so if we have a PSD matrix, we sometimes will use this notation. So we have this curly notation here, right? So we just say A with this curly notation greater or equal than 0, and that means that A is PSD. And in general, you can even write it as, so here as this name says, some order. So this is so-called partial order. So you can say A is greater than B. And that simply means that A minus B is positive semi-definite. Right? So if you set B to 0, B to 0, you just have what we have here. Okay, so this is a notation that we will be using sometimes. Now that we have defined the concept of eigenvalues, I told you eigenvalues are defined for square matrices. Let's look at a more general case where we have a rectangular m by n matrix. So we have our m by n matrix, and we'd like to define the concept of an eigenvalue. So what can we do? Well, we could just create a square matrix. So what we're going to do is just say, create a square matrix, right? So if you have A is an m by n matrix, A transposed is going to be an n by m matrix. So when I multiply, right, when I do A transposed, I get an m by n times an n by m. So this is going to be an m by m matrix. And here, what I can just do to define these singular values, which we denote here by this sigma of I, we just take the eigenvalue of the square matrix here, which is an m by m matrix, which we created. Equivalently, you can create A transpose A, and this will have dimension n by n. So this is what we are saying is that this is equivalent. Important to note, though, is that because this is an m by n matrix, the number of non-zero singular values is at most equal to the rank, and the rank is a minimum of m and n, okay, of the two dimensions. And I already mentioned this before. Another remark is that the largest singular value, which we again here will denote by sigma 1, is equal to the operator norm of A, right? So you remember we defined the operator norm of A as saying this is the supremum of AX divided by the norm of X, right? And this was for all vectors X in RD except the 0 vector. Okay, and we said that this is equal to sigma 1 of A. All right. So now that we have defined the concept of a singular value, I'd like to discuss a tool that is useful to decompose matrices. And this is the so-called singular value decomposition. So what do we do with the singular value decomposition? We start from an m by n matrix, which is our A matrix here. And we decompose this into three matrices, into the product of three matrices. So we have a first matrix U, which is a square matrix, which is an m by m matrix, right? So it matches this dimension here, times a diagonal matrix. Well, it's an m by n matrix, and it has so in the picture here, essentially this part is going to contain the singular values. I'm going to explain this soon. So we have this D matrix in the middle, and then we have a V transpose matrix here. And this one has dimension n by n, right? So n by n here. So you can check, of course, that when you multiply all those things, you get the right dimension. So what are those matrices U and V exactly? So those are so-called orthogonal matrices. And what that means, as a reminder, an orthogonal matrix is a matrix such that if you do U transpose U is equal to U transpose is the identity matrix. And the same holds for the V matrix, right? V transpose V times V transpose is the identity matrix. And again, D, as I said, it's a diagonal matrix, which is padded with zeros. So this part here, right? This part will have zeros. Okay. All right. Very briefly, I want to again just rediscuss the definition of orthogonal matrices. So first of all, we said that two vectors are orthogonal if their inner product is equal to 0. Okay, so this is what it means to have orthogonal vectors. And an orthogonal matrix, if you want, is a generalization of it. So I told you it satisfies this definition. And what you can do is that you can write what that means for the when you look at the rows or the columns of this matrix. So if you denote here by AI let's say the columns of the matrix, essentially you have this property that two columns multiply each other. So their product is equal to 0 if I is equal to j, right? So this delta here, let me redefine it. It says that this is equal to 0 if I is not equal to j, and is equal to 1 if I is equal to j. Okay, so that's what it means to have an orthogonal matrix. You can look at the product of the columns or the rows, and it has to satisfy this equation here, and you can again put it back in the matrix form, and you get what I discussed before. Small note on the inverse in the orthogonal matrix, essentially because of the definition, right? You have A transpose equal to I. That's easy to see that it means that A transpose is equal to the inverse, okay? So as I mentioned before, right? So essentially we are taking a matrix A and we decompose it into this product, U times D times V transposed. And in this D matrix here, right? So it contains the singular values, okay? So D is a diagonal matrix. I already mentioned this before. It has at most rank, so the most rank number of singular values, and the rank is upper bounded by the minimum of m on n. And then by convention, essentially we have the same convention as before. We sort them, right? So we said sigma 1 again is the largest. This is the smallest. They are all non-negative. This is important to note. Eigenvalues could be negative, but in the case of singular values, they are non-negative. Right? And I mean, you see it from the definition again, right? I told you the definition is sigma I of A is equal to the square root. So of course, square root, we need a positive number for real matrices. We have this, right? So this by the definition, it's clear to see that they have to be non-negative. But they can, of course, be equal to 0. And then, so as I said, so this D matrix contains the singular values. The U matrix, if you look at here, the columns of this U matrix, these columns are the so-called left singular vectors. And if you look at the rows of V transpose, or the columns of V, these are the so-called right singular vectors. Okay. And they form a basis. So they form an orthogonal basis for the row space of A, for instance. All right. So we have this decomposition, which will be a useful tool. You can, if you want also, what you can do is, again, let me rewrite the SVD decomposition. So we said that A is equal to U dV transposed. And here what I'm saying is that if you multiply the SVD by V, if you multiply by V here on the right, so if you do A times V on the right, you get U d V transpose V. And of course, this V transpose V is just identity, right? So you just get that this is equal to U times D. And you can actually write this also in this way, right? So this is a product of two matrices, but you can write that if you take, again, we said the VI's at the columns of the matrix V, you can write it in this way. And you can do the same here for, so for A transpose, you can multiply it by on the right by U, and you will find this is equal to VD transpose, which is equal to this equation here. And so this is another way if you want to write what it means, right? So now you can see that the matrix A is acting on the column of V, which is one, as we said, right? These are the so-called right singular vector. So we see that when A acts on the right singular vector, you get U. And here it's similar. When you do A transpose times U, which is the left singular vector, you get V. Okay, so this is sort of dual relation compared to what we had before, right? So before for the eigenvalues, we said that AV is equal to lambda V, right? So the vector V here was the same, and now you can see now it has changed. Okay. All right. And finally, just to discuss some interpretation of the SVD. So what you can do is that you can start from, let's say you start from a unit circle. So you apply A to these two vectors, let's say to the red vector and to the blue vector, right? Which are just some, let's denote this by E1, right? So and this by E2, right? So you remember I said before, those are the standard basis vectors, let's say for R2. And you apply the matrix A, and then you can see that this will essentially apply some sort of transformation to these two vectors, right? So here I will obtain that E1 is not this vector, and then E2 is this vector. So this is, this will be essentially E1 prime, and then E2 prime, right? And so E1 is prime essentially is A times E1, right? So this is the new vector that I get once I apply the transformation with this matrix A. But what I can do is I can decompose this matrix A using the SVD, right? So we said A is equal to U D V transposed. So what I can do is that I can actually understand essentially a transformation here when I do, so this is equal to U D V transpose E1. I can first understand it as taking my vector E1 and applying the matrix V transpose to it. So this is what we have here. Right, so V transpose, let me use some color in green. So we apply first this to the vector E1. Because these matrices, as we said before, are orthogonal matrices, this corresponds to applying a rotation. So here what you can see is this means applying a rotation. So I take my two vectors and I rotate them, okay? Then once I've applied this V transpose to E1, I apply D. So now I apply this matrix D, which is this transformation here. D is diagonal. So because D is diagonal, the only thing we can do is we can only stretch the different directions. So this corresponds to do a scaling. We are just scaling the different directions. And you can see here on the figure, what we have done is we took this circle and we made it to be an ellipse. So we elongate this in just the two directions. And finally, what is the last transformation? So we said that we apply the vector, the matrix U. And this is again a rotation matrix. So it just simply means that we apply another rotation as well. Okay. So essentially, then you can understand this, this transformation of two vectors by this matrix A as applying a rotation, followed by a scaling, followed by another rotation. So this is a way to decompose essentially what happens when you apply a matrix to a vector. As an exercise, I'll conclude with this. You can try to show that if the matrix A is symmetric, the singular values correspond to the absolute values of the eigenvalues, lambda I. So essentially proving that this holds. And for this, you can try to, so a hint is you can actually use this decomposition, and then, write down the definition, right? So it gives you a definition, you can write it down and try to use essentially combine these two things, right? So, and then you will see that you should be able to derive this equality here that I just mentioned. Okay, so this ends this section on linear algebra.